Welcome to a lesson on triple integrals and volume using cylindrical coordinates. The goal is to determine the volume of a solid using cylindrical coordinates. In a cylindrical coordinate system, a point P in space is represented by an ordered triple r, theta, and z, as we see here below. R theta is the polar representation of a point in the xy plane, where r here is the directed distance from the origin in the xy plane, and theta is the angle counterclockwise from the polar axis or the positive x-axis. And z is the directed distance up or down from r theta in the xy plane. And then also we need to be familiar with the formulas used to convert between rectangular and cylindrical coordinates, as we see here and here. So to determine the volume of a solid using cylindrical coordinates, we're going to have a triple integral over the region V integrated with respect to V, where differential V is equal to r dz dr d theta. Remember, we have an extra factor of r, and then the limits of integration will be expressed using r and theta. And this is very similar to what we did in the previous video when we introduced triple integrals using cylindrical coordinates. Let's go and take a look at that real quickly. The only difference is, for the volume, f of x, y, z would be equal to 1. So our procedure for evaluating the triple integral is going to be the same as we did in the first video. It's just that now the limits of integration will define the solid region, which will then give us the volume of the solid using this triple integral. Let's go and take a look at our first example. Here we want to use a triple integral in cylindrical coordinates to determine the volume of the solid bounded by z equals 0 and z equals 9 minus the quantity x squared plus y squared. Let's take a look at this in 3D first. So here's our graph. We have a paraboloid in blue, and then we have this yellow plane, and our goal is to determine the volume inside the paraboloid above the yellow plane. So we'll start by taking a look at the xy, xz, and yz traces. So for the xy trace, we'll set z equal to 0. So if z was 0, we could move the quantity x squared plus y squared to the left side, and we'd have x squared plus y squared equals 9. So we have a circle centered at the origin with a radius of 3. And then for the xz trace, if we set y equal to 0, we'd have z equals 9 minus x squared. Well, that's a parabola that opens down with a z-intercept of 9 and x-intercepts of positive 3 and negative 3. So it would look like this. And then the yz trace is similar. If we let x equal 0, we'd have z equals 9 minus y squared. So if this is the y-axis and this is the z-axis, the trace would look just like the xz trace. So our volume is going to be equal to the triple integral, where differential v is going to be equal to r dz dr d theta. So we'll start by determining the limits of integration for z. And for the xz and the yz trace, I might as well go ahead and graph z equals 0 here and here. So we can see that z starts at 0, and then for the upper limit of integration with respect to z, which must be expressed in terms of r and theta, would be determined by these two parabolas here, which were slices of z equals 9 minus x squared plus y squared. And since x squared plus y squared is equal to r squared, we'd have 9 minus r squared for our upper limit of integration for z. And then to determine r, we can look at the xy trace. R is going to start at 0 and then go out to 3. And then for theta, we need to go all the way around this circle, so it'd be from 0 all the way to 2 pi. So this triple integral will give us the volume of this bounded three-dimensional region. Let's go ahead and evaluate this on the next page. We'll first integrate with respect to z, treating r as a constant. That's going to give us rz. Well, when z is equal to 9 minus r squared, we'll have 9r minus r cubed. And then when z is 0, this will be 0. Now integrating the respects to r, we're going to have 9 times r squared over 2, or 9 halves r squared, minus r to the fourth over 4, or 1/4 r to the fourth. So when r is 3, we're going to have 9 times 9 is 81 over 2, minus 3 to the fourth is 81, so 81 fourths. And then when r is 0, these will both be 0. (81 halves minus 81 fourths will equal 81 fourths. Integrate with respect to theta. So we'll have 81 fourths times 2 pi over 1 and minus 0. This simplifies here. So this would be 81 pi over 2 cubic units for the volume of this solid region. Let's take a look at one more example. We want to use a triple integral in cylindrical coordinates to determine the volume of the solid bounded by z equals 4 minus the square root of x squared plus y squared, x squared plus y squared equals 1, and z equals 0. Let's go and take a look at this graphically. So the goal is to determine the volume inside the cylinder above the green plane and below the blue surface. So let's start by taking a look at the traces. Let's take a look at the xy, xz, and yz traces. So for the xy trace, we'll let z equal to 0. So if z is equal to 0 here, we'd have 0 equals 4 minus the square root of x squared plus y squared. So if we move this square root to the other side and then squared both sides, we would have x squared plus y squared equals 16. But we're not actually going to use this trace because if we take a look at the other trace, x squared plus y squared equals 1, we're looking for the volume that's inside this smaller cylinder, so we're only going to sketch the circle with radius 1 centered at the origin. So here's our xy trace that we need. For the xz trace, we'll set y equal to 0. Be a little careful here. We'll have z equals 4 minus the square root of x squared, which would simplify to the absolute value of x. And then here we'd have x squared equals 1. And here we have z equals 0. So here's z equals 0. For z equals 4 minus the absolute value of x, remember absolute value graphs make a v, so this will be a v with a z-intercept of 4, something like this. Then x is equal to plus or minus 1. So the xz trace is this region in here. Here we had inside the circle. Then the yz trace is going to be similar to the xz trace. Setting x equal to 0, we'll have z equals 4 minus the absolute value of y. Here we'll have y squared equals 1. And again, z is equal to 0. So here's z equals 0. Here's y equals negative 1. Here's y equals positive 1. And we have this v-shaped graph from the absolute value. So our region is in here. A lot of times when setting this up, we only need the xy trace, but I think getting in the habit of making all three traces is often helpful to get a better understanding. So our volume is going to be equal to this triple integral where we have r dz dr d theta. So for the limits of integration for z, it starts at 0, and then it goes up to these v-shaped graphs that are generated by this cone z equals 4 minus the square root of x squared plus y squared. Remember, we have to express z as a function of r and theta. So the upper limit for z is going to be 4 minus, this will be the square root of r squared, or just 4 minus r. And then for r and theta, we can use the xy trace. R will be from 0 to 1. Then theta will be from 0 all the way around to 2 pi. So let's go ahead and evaluate this on the next page. So we're going to have r times z. Now we'll replace z with 4 minus r and then with 0. Replacing z with 4 minus r, that'll give us 4r minus r squared. And then when z is 0, this will be 0. Integrating this back to r, we're going to have 4 times r squared over 2, or 2r squared, minus 1/3 r cubed. Replacing r with 1, we're going to have 2 minus 1/3. And then when r is 0, these will both be 0. 2 minus 1/3 is 5/3. So we'll have 5/3 theta. We'll have 2 pi, I'll put it over 1 minus 0. We have 10 pi over 3. So the volume of the solid inside the cylinder, above the green plane, below the blue surface, is equal to 10 pi over 3 cubic units. And that'll do it. Thank you for watching.